Hello, welcome to my online lecture on game theory. For this lecture, I will be using a slide, so I hope you can open the slide and follow me through the slides. Okay, so first, let me define what game theory is. Game theory is the study of mathematical models of conflict and cooperation between intelligent, rational decision makers. If I were to put it simply, it's the mathematical study of competitive games. And later on, we will be defining what are the composition of a game. Okay. However, let me start off by giving you an example. I'm not sure if everyone has already seen the movie A Beautiful Mind. It's the biography of John Nash. A mathematician who founded a lot of theories, but for this particular lesson, he actually started game theory. He founded game theory. Now, in the next slide, there is a video clip of the movie A Beautiful Mind, where it actually shows the general idea of game theory. So what I'd like you to do is to go through the movie and watch it and listen to the conversation. Okay, I will give you time next time to ask questions or discuss the movie with me. Now, another good example that I can use to discuss game theory is what we call the prisoner's dilemma. The prisoner's dilemma is a popular example being used by a lot of economics teachers all around the world whenever they try to discuss or at least introduce game theory. So let me tell you a brief idea about the prisoner's dilemma. So in the prisoner's dilemma, there are two prisoners. So let's start with two criminals. Let's say these two criminals are robbing a bank. There are two criminals robbing a bank, and let's say they were caught by the police. Okay, so let's say we have prisoner A and prisoner B. Okay, so they were caught by the police. They were brought to the precinct, and they were placed inside an interrogation room. Now, let's say the police, in the interrogating these prisoners, have circumstantial evidence that these prisoners are also also did a more heinous crime. Let's say they murdered someone. However, the police right now only have circumstantial evidence, and therefore they couldn't pin the murder on these two prisoners. So what the police are trying to do during the interrogation is they're trying to let these two prisoners admit to the murder. They were caught for the robbery, but the police is trying to pin them down for the murder. So because they are in the interrogation room and that these two prisoners, even though they cannot talk to each other, can see each other, they are placed in a situation where it is beneficial for both prisoner A and B to stay silent. Why? Because staying silent for both prisoner A and B is a way of communicating. If prisoner A stays silent, it is a way for prisoner A to say or communicate to prisoner B, look, I'm staying silent, I'm not ratting you out, so you better also stay silent. In the same way, because prisoner B is in the same room, and he sees that prisoner A, or hear that prisoner A is not saying anything. Therefore, prisoner B also thinks rationally and sees that it is actually better to stay silent and just be jailed for the minor crime, let's say robbery. Okay? Now, in this situation, mathematicians usually say that the best scenario is for the police to put these two prisoners in two separate rooms. Okay? So two interrogation room where prisoner A and prisoner B do not have any contact at all. Okay? And if these two prisoners are placed in two interrogation room, essentially they still have the same two decision that they can make. either to stay silent or to confess. Okay? And for prisoner B to also stay silent or to confess. Okay? Right now, prisoner A and prisoner B are staying silent. No, when they were placed in the same interrogation room, because they know that no one is talking, therefore they're staying silent. And let's say because of the robbery, they will just get 2 years. And I'm putting here -2 because obviously being placed in jail is a negative thing for prisoners, and therefore that's negative. And 2 is the number of years. Okay. -2 here is the amount of years prisoner A will have, and -2 here is the number of years prisoner B will have, okay, or will get. Now, what will happen if prisoner A stays silent, however prisoner B confesses? Because prisoner B will confess, and most probably when he confesses, he will rat out on prisoner A, saying that prisoner A is an accomplice to the murder. Then prisoner A will get, let's say, 20 years. Okay? And because prisoner B confesses, let's say he will not get any jail time, and probably become a state witness. At the same time, if prisoner A confesses and prisoner B stays silent, it will be the same scenario but opposite. And therefore, prisoner A will not get any jail time and prisoner B will get 20 years in prison. However, if both prisoner A and prisoner B confess, then let's say because they both confess, they will not get the maximum term of -20, and let's say the police can work out a deal with the judge and just get them, let's say, 12 years each. Okay? Now, if you try to see this scenario, if the two prisoners are both in the same room, then the optimal solution for them is to stay silent. Because by staying silent, they will just get each 2 years. Right? And because they are in the same room, then it's easy for each one to know if the other prisoner is ratting him or her out. Okay? However, because the prisoners are placed in 2 separate rooms, then you get rid of any communication between the two. And in this case, you are putting these 2 prisoners in a scenario where, from this optimal solution, you are actually making the optimal solution for both prisoners to confess. Why? Because if the 2 prisoners are in 2 separate rooms, then imagine you're prisoner B and I'm prisoner A. If I stay silent, and because I don't know what's happening with prisoner B, I will think, maybe prisoner B is ratting me out. And because if prisoner B is ratting me out and I stay silent, then we will get this scenario where prisoner B will get 0 jail time and I'll get 20 years. In the same way, in the point of view of prisoner B, if prisoner B stays silent, he will also think, what is happening to prisoner A? Is he ratting me out? If prisoner A is ratting me out, then we will be placed in this scenario where prisoner A will get 0 and prisoner B will get 20 years. And because of that element that prisoner A doesn't know what prisoner B is doing, and vice versa, then this is where we're moving the optimal solution from both being silent to both confessing. Now, this prisoner's dilemma is actually a classic example of game theory, and this is what we call a two-person non-zero sum game. I will tell you why this is a non-zero sum game, but I hope it's very obvious that this is a two-person game. No? There are 2 persons involved in the game, prisoner A and prisoner B. Okay? Now, if the prisoner's dilemma is a two-person non-zero-sum game, for our lesson, we will be focusing on a different model, and this model is called a two-person zero-sum game. Okay, and this two-person zero-sum game has two elements. First, two-person. What do we mean by two-person? The requirement for this two-person is that we have two entities, or what we call players. Okay? These entities or players doesn't have to be people. They can be companies, or they can be corporations, they can be strategies, etc., etc. As long as you can identify these two entities, then it will suffice. Now, these two entities have to be rational. What do we mean by rational? In mathematical terms, being rational means either maximizing some benefit, or you can also minimize some cost. Okay, and that is what being rational means. Okay, the other assumption of these two entities is that these two entities have to be greedy and selfish. I think this supports the first assumption of being rational, because let's assume you have two options, option A and option B, and let's say if you choose option A, you'll earn 50, and if you choose option B, you'll earn 30. Now, in both options, you will earn. But because you are rational, meaning you'd like to maximize, and you are greedy and selfish, then if you have the choice between option A winning 50 and option B winning 30, you will always choose option A. Okay, and that's the assumption of these two entities. Now, in this competitive scenario, the game has to be zero sum. And what do we mean by zero sum? When we say zero sum, literally means the sum of the winning of player 1 and player 2 is equal to 0. Okay? As you can see a while ago in the example of the prisoner's dilemma, if you remember staying silent for prisoner A, prisoner number 1, and prisoner number 2 staying silent as well, no? the payoff, or the number of years they will get each, is -2 and -2. And in this case, it is very clear that the sum of the two winnings is not 0. Okay? And that is why that prisoner's dilemma example is actually a two-person. So you have two prisoners, two entities, but the game is non-zero sum. Okay? Now, just to give you an idea of a zero-sum game, let me show you a quick example. Some quick generic example. Let's say you have player 1, and you have two strategies, and you have player 2, and let's say you have two strategies again. Okay? And let's say this is 2, -2, this is 0, 0, this is -3, 3, and this is 5, -5. Okay? In this example, quick example, we can see that this is actually a two-person zero-sum game. Why? There are two elements, or two entities in the game. You have player 1 and player 2. They have two strategies. This is strategy A of player 1, strategy B of player 1, strategy A and B of player 2. And if you look at the payoff, one is positive and the other one is negative, no? Or both are 0, and the sum is 0. And therefore, this is a zero-sum game. One classic example of a two-person zero-sum game is actually Jack and Poy. Let me use that example so that everyone is quite familiar with Jack and Poi. With the example. Okay, so in Jack and Poi, there are two players. Again, you have player 1 and player 2. And player 1 has three possible strategies. He can either show a rock, a paper, or a scissors. Okay? And for player 2 also has the same set of strategies. Player 2 can either show a rock, paper, and scissors. Okay? Now, let's say winning a Jack and Poi game gains the player 1 point and losing nets a player -1 point. Okay? A draw is 0 points, let's say. Now, we can quickly generate the payoff in this table. If player 1 and player 2 shows rock, then it's a draw, and therefore the payoff for both is 0. However, for rock and paper, paper wins, and therefore this is -1 and 1. Player 1 loses, and therefore he gains -1 point, and player 2 wins, and therefore he gains 1 point. Okay? And if player 1 shows rock and player 2 shows scissors, then this is 1, -1. In the same way, let me just quickly fill this table up. Paper rock, paper wins, so this is 1, -1. Paper paper is a tie. Paper scissors, scissors win, so this is 1, -1, 1. And finally, scissors rock, rock wins, so -1, 1. Scissors paper, scissors win, 1, -1, and scissors scissors is a draw. Okay, so this is your game theory representation of Jack and Poi. Okay, and let me take this instance to show you the three different components of a game theory problem. Let me encircle. 1, 2, 3. Okay? So, what are the three components of a game theory problem? These are the strategies of player 1. These are the strategies of player 2. And this is your payoff table. Now, I'd like to represent this payoff table in a different manner, in a smaller manner, and yet it will hopefully mean the same thing. Okay? Okay, so again, we still have player 1, and we still have player 2, and we still have the three strategies for each player: rock, paper, scissors, rock, paper, scissors. Okay? And if you remember, in the first, in this first cell, you have 0, 0. Okay? And for the second cell, for this cell, rock loses to paper, therefore this is -1 and 1. Okay, I will not finish the entire table because we're trying to reduce the payoff table to a smaller payoff table. Now, what will happen here is instead of writing 0, 0 and writing -1 and 1 here, what I will do is to simply write 0 and -1. And to continue the entire table, rock and scissors, rock wins, therefore this is 1. Paper, rock, paper wins, therefore this is 1. Paper, paper, it's a draw. Paper, scissors, paper loses. Scissors, rock, scissors loses. Scissors, paper, scissors win. And scissors, scissors, it's a draw, then we have this payoff table. I hope you understand how we were able to reduce the payoff table a while ago into this payoff table. Essentially, we just need the payoff of player 1 because of the assumption, because of the zero-sum assumption. Because we know that the game is zero-sum, then if you have a payoff of -1 here, and this is in the point of view of player 1, then we also know that the payoff for player 2 is 1. Okay? So this means -1, 1. This means 1, -1. And this one means, obviously, 0, 0. So on and so forth. Okay? Now, from now on, you have to learn how to see game theory problems in this manner, where you don't actually see the payoff of both player 1 and player 2. Okay? Dapat masanay na kayo na isang number lang. And in this case, the number here will represent the payoff in the point of view of player 1. Okay? Now, before we actually go to the details of game theory and how we actually solve game theory problems, let me first tell you two assumptions that are very important when we look at game theory problems. What's the first assumption? The first assumption is that, for example, let's write back the rock, paper, scissors, jack and poi payoff table. Okay, so this is a 0, 0, 0, rock, paper, paper wins, rock, scissors. This is 1, -1, 1. Okay, now, the first assumption in game theory is that this payoff table is known to both players. Okay, so in the point of view of player 1, what player 1 sees is this. Why? Because these numbers are the payoff of player 1 in the game. Okay? Depending on the pair of decisions that were made by both player 1 and 2. Okay? But these numbers are in the point of view of player 1. Now, what does player 2 see? So if we convert this payoff table in the point of view of player 2, so we'll put player 2 here, and we'll put player 1 here, obviously we have the same strategy, rock, paper, scissors, rock, paper, scissors. Okay? Again, rock, rock, draw, 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 rock, paper, paper wins. Let me see if it's correct. Scissors, rock, rock wins. Okay. Scissors, paper, scissors win. Okay. Now, what happened here is we converted this payoff table, which right now is in the point of view of player 1. We converted this payoff table to a payoff table that is now in the point of view of player 2. It just so happened that the payoff table is the same. Okay? However, what is more important to note right now is that when we try to discuss game theory problems, whoever is in the row player, that is the point of view of this payoff. Okay? So, quickly, let's say we have this payoff table. Okay, so if this is in the point of view of player 1, okay, and this is player 2, now we can actually convert this payoff table into the point of view of player 2. Sorry. So in the point of view of player 2 has 3 strategies, 1, 2, and 3. Player 1 has 2 strategies, A and B. Okay? And if player 2 does 1 and player 1 does A, that's essentially this 3. But because 3 is in the point of view of player 1, then in the point of view of player 2 loses 3. Okay? In the same way, this 1 and B is actually this, but in the point of view of player 1, it's player 1 will lose 4. Therefore, if we convert it to the point of view of player 2, then player 2 wins 4 because of the assumption of zero sum. And if we quickly fill up this table, then this is -2, -1, -1, and 5. Okay? So what happened? If this is the payoff table in the point of view of player 1, to be able to see what player 2 sees, all you have to do is transpose and negate. What do we mean by transpose? This becomes this and then negated. Why negated? Because whatever one wins or one loses here, the other one loses or wins here. Okay? And that's why it's negated. If you look at this example and transpose it, so every column here becomes a row, and if you negate, so your 0, 1, -1 becomes 0, -1, and 1, -1, 0, and 1 becomes 1, 0, -1, etc. You will now see the perspective of the other player. Okay? But the assumption still remains the same, that the payoff table, whether seen in the point of view of player 1 or seen in the point of view of player 2, the assumption is that both players know the payoff table. Okay? Now, the second assumption assumes that in a game, both player will have to choose a decision simultaneously. So, as you know, whenever you play Jack and Poi, and whenever you have an opponent, you have to, diba? You have to show a figure, no? Whether rock, paper, or scissors at the same time. You cannot say, okay, let's say you are my opponent. You cannot say, you show first what you will be showing, and then I will show mine after. Hindi pwede yun, no? Obviously. Okay? So the second assumption is that in an actual game, both players will actually have to simultaneously show a decision. Okay? Now, before we actually start solving game theory problems, let me first define a term that I will be using all throughout the lesson. Okay? And what is this term? This term is called dominated strategies. Now, what is dominated strategy? You can read through the slide. But what is dominated strategy? Dominated strategy is a strategy such that there is another strategy that is at least as good whatever the opponent does. Okay? Again, a dominated strategy is a strategy such that, it takes time to erase, such that there is another strategy that is at least as good whatever the opponent does. Okay. Now, to quickly explain the concept of dominated strategy, let me use this example. Okay, let's say you like to travel, and let's say you are choosing between Hong Kong, USA, and let's say Japan. Okay? Now, let's say whenever you travel, it is for both business. You have, in a way, two criteria. One is for business, and the other one is for leisure. Okay? And let's say, just for the sake of simplicity, the higher the number, the more positive the number, the higher the benefit it is for you to go to that country. And let's say right now this is just 20, and let's say this is 60, and let's say this is 40, and let's say this is 30, and let's say this is 90, and let's say this is 80. Okay? So what does this mean? This means that in the point of view of business, if you go to Hong Kong, you'll get some 40 points. But in the point of view of pleasure, let's say sightseeing, tourist attractions, shopping, let's say you'll get 30 points. Now, if you go to the US, you get 20 and 60 for business and pleasure. And if you go to Japan, you'll get 90 and 80. Okay. Now, to explain the concept of dominated strategy, let me first focus on Hong Kong and the US. Okay? Now, let's say you are choosing between Hong Kong and US only first, no? And you'd like to see, is there an option that is nicer, no? Which that is surely nicer than the other. Okay? Now, if you compare Hong Kong and US in terms of business, Hong Kong is better. Okay? On the other hand, if you look at your trip in terms of pleasure between Hong Kong and US, US is better. And this is a scenario where there is no option that is a clear winner. Okay? So between Hong Kong and US, Hong Kong is better for business, US is better for pleasure. And therefore, there's no clear winner. Now, let us focus our attention, let's say Hong Kong and Japan. Okay? So we'll focus on Hong Kong and Japan right now. Now, for Hong Kong and Japan, in terms of business, so let me erase the check mark. In terms of business, between Hong Kong and Japan, you'd rather go Japan because 90 is higher than 40. And in terms of pleasure, between Hong Kong and Japan, again, 80 is higher than 30, therefore you'd rather go to Japan than Hong Kong. And as you can see, if you're comparing Hong Kong and Japan, then Japan is the clear winner. Why is Japan the clear winner? Japan is better in terms of business and better in terms of pleasure. And because you're comparing the two and Japan is the clear winner, then we can say the Hong Kong option is dominated. Okay? The Hong Kong option is dominated, and this option is dominated by the Japan option. Okay? In the same manner, if we now compare Japan and US, okay? In terms of business, Japan is higher than US in terms of business, so we will choose Japan. In the same way, Japan's pleasure points is 80 versus US pleasure points is 60. Therefore, we will choose Japan. Again, we see a scenario where Japan dominates the US option. And therefore, in your point of view, you will not pick US. Okay? And this is a way to understand dominated strategies. What you're trying to do is you're trying to look for a strategy such that there is another strategy that is always at least as good. So look at this. If you compare Japan and Hong Kong, Japan is always at least as good, whatever the scenario is, whether it's for business or for pleasure. Japan also trumps US in terms of business and pleasure. Okay? Now, what I will do right now is I will give you a generic payoff table, and let's try to identify dominated strategies. Okay, so let's try to apply the concept of dominated strategy in this example. So let's say you have player 1 here, and player 1 has two strategies, or have two strategies, A and B. And let's say player 2 has three strategies, labeled as 1, 2, and 3. Okay? This is 40, 30, 50, negative 20, and 40, 60. Okay? Now, just for the sake of this example, let's say we will also like to see the payoff table in the point of view of player 2. So let's have that below. Okay? So we'll have player 2 here. We'll have 1, 2, and 3. We'll have player 1 here. We'll bring it lower. We'll have A and B here. Okay? And again, as discussed a while ago, if you wanted to convert this payoff table into the payoff table in the point of view of player 2, all you have to do is transpose and negate. So 40 and 30 becomes negative 40 and negative 30. 50, negative 20 becomes negative 50 and positive 20. 40, 60 becomes negative 40 and negative 60. Okay? Now, our goal right now is to identify dominated strategies. Now, normally in class, I will ask you to look for dominated strategies. But because this is an online lecture, let me show you the dominated strategy. Okay, compare strategy 1 and 3. Now, if you'd like to compare strategy 1 and 3, remember strategy 1 and 3 are both are player 2 strategies. Okay? So you are actually comparing 40, 30, 40, and 60. Now, if you remember the definition of dominated strategies, the definition, let me repeat again. A dominated strategy is a strategy such that there is another strategy that is at least as good, whatever the opponent does. So look, if you're comparing 1 and 3, so whatever the opponent does, we have to see if 1 is always better than 3 or 3 is always better than 1. Okay? So if player 1 chooses A. Now, if player 1 chooses A, what will be the choice of player 2? Now, so player 1 chooses A and you're comparing 1 and 3. So we're looking at these two numbers. Remember the Hong Kong, USA, and Japan example a while ago? In this case, these two numbers are the same, and therefore, what you can say is you are indifferent. Or, you can choose either 1 or 3. No? Now, on the other hand, if player 1 chooses B, so if player 1 chooses B and you're still comparing 1 and 3, then you're looking at these two numbers, then what would you rather have? A 30 or a 60? One careless mistake is choosing 60. Okay? However, that's a mistake. Why? Because remember, the two strategies that you're comparing, strategy 1 and 3, are player 2 strategies. And the payoff table you are using is in the point of view of player 1. Therefore, this 30 actually, in the point of view of player 2, is a win for player 1 or a loss of player 2. This 60, which is a win for player 1, is actually a loss of 60 for player 2. And that is being supported by this transformed payoff table in the point of view of player 2. Look at 30 and 60. It became actually negative 30 and negative 60. So in the point of view of player 2, what would you rather have if player 1 chooses B? Would you rather lose 30 or would you rather lose 60? And in this case, I think because of the assumption of rationality and then selfishness and greediness, then player 2 will choose 1. Okay? And because player 2 chooses 1, if player 1 chooses B, and because player 2 will either choose 1 or 3, if player 1 chooses A, then we can technically say 3 is dominated. Why? Because even if player 1 chooses A, you are indifferent, it is very obvious that if player 1 chooses B, you won't choose 3. So might as well cancel strategy 3 altogether. Okay? So technically in player 2's point of view, negative 40 and negative 60 is cancelled. But because player 1 knows this payoff table and player 1 also knows that player 2 is rational, selfish, and greedy, then player 1 also knows that this column is dominated. Okay? Next. Now, because strategy 3 is dominated, then we can now compare A and B. These two. Now, these two strategies are strategies of player 1. So, who is the opponent? The opponent is player 2. So, whatever the opponent does, one should be better than the other. And let's see. Okay, so we have if player 2 chooses 1, what will happen? Look, if you're comparing between strategy A and B, and if player 2 chooses 1, you actually have a choice between gaining 40 or gaining 30. And I think it's very obvious that player 1 will do A. Okay? Next, if player 2 chooses 2, okay, so let me write that. If player 2 chooses 2, then you're comparing 50 and negative 20. And I think it's very obvious that you'd rather win, player 1 would rather win 50 than lose 20. And therefore, player 1 will also choose A. And in this case, I think this is a nice example of a dominated strategy. Player 1 will never choose strategy B. And because player 2 knows this table, albeit in a different perspective, not transposed and negated, and because player 2 also knows that player 1 is rational and greedy, then player 2 also knows that player 1 will remove strategy B. Okay? In the end, we have the same payoff table, albeit negated and transposed. Now, finally, what we can do is we can now compare 1 and 2 again. Okay? We're comparing 1 and 2 strategies of player 2. Therefore, the opponent is player 1. So, if player 1 chooses, in this case, in the point of view of player 1 only has a single strategy available. So, if player 1 chooses A, then what will happen? Player 2 has the choice between losing 40 or losing 50. And in this case, because losing 40 is better than 50, player 2 chooses 1. And because player 1 doesn't have any other strategy available, then it is clear for player 2 that strategy 2 is dominated. In the same way, if this is dominated, this is also dominated. Okay? What we end up with is a single value, 40 or negative 40, depending on the point of view. And this is your optimal payoff. Okay? What do we mean by the optimal payoff? It's the payoff of the game at the optimal solution. And what is the optimal solution? For player 1 to do A and player 2 to do 1. Okay? Or, in order to write this mathematically, I will write it this way. Player 1 equals 1, 0. Okay? Sorry. Let me move this. Player 1 choosing A means this. Player 2 choosing 1 means this. Let's try to understand. What is 1, 0, 1, 0, 0? Player 1 choosing A means the probability that player 1 will choose A is 100% or 1, and the probability that player 1 will choose B is 0%. Okay? So, saying that the optimal solution is player 1 choosing A mathematically looks like this. In the same way, player 2 choosing 1 means the probability of doing strategy 1 is 1, and doing strategy 2 and 3 are 0. Okay? Now that you have an understanding of dominated strategy, then let us now apply the concept in a different example. Let's say again you have two players, so player 1 and player 2. And let's say for player 1 has three strategies, A, B, and C. And again for player 2, let's say he has three strategies again. And let's say the corresponding payoff table looks like this. You have 20, 15, 50, 40, 10, negative 30, negative 10, 5, and 65. Now, what I'd like you to do is I'd like you to look for dominated strategies. One technique in looking for dominated strategy is to simply go through each pair of strategies and check if there's a dominant one. So let me show that to you quickly. Let me compare A and B. A and B, this is lower than this, so lower, higher. Because 20 is lower than 40 and because 15 is higher than 10, then there is no sure winner anymore. Okay, so we can skip checking A and B. Let's check A and C. Higher, 20 is higher than negative 10. Higher, 15 is higher than 5. Lower. So higher, higher, lower. So there is no clear winner between A and C. Let's check B and C. Higher, higher, lower. So again, there is no clear winner between B and C. So you've actually checked all possible pairs of player 1 strategy. So we can now go to player 2. We'll compare 1 and 2. For 1 and 2, this is higher, higher, lower. So again, there's no clear winner between 1 and 2. Let's compare 1 and 3. Lower, higher. So there's again no clear winner. Let's compare 2 and 3. Lower, higher. Again, no clear winner. Now, in this case, we are now presented with a payoff table where you are not able to reduce the size of the payoff table to a single strategy for each player. Okay. Unlike in the previous example that we discussed, we were able to pin down the single strategy for both players. No? If you remember, for player 1, it is to do A, and for player 2, to do 1. Okay? However, in this case, no matter how much we try, we cannot reduce the payoff to a single cell. So what do we do now? Does it mean there's no optimal solution? Wrong. What we will do now is to apply what we call the maximin criterion. Okay? And what is this maximin criterion? I usually don't like to use the word worst case scenario, but to easily understand the maximin criterion, all you have to do is think, what is the worst case scenario for each player given a certain strategy? And let me show that to you. Now, for player 1, player 1 has 3 strategies, A, B, and C. If player 1 chooses A, okay, if player 1 chooses A, so these are the 3 possible outcomes. No? If player 1 chooses A, what is the worst case scenario? The worst case scenario is for player 2 to choose 2. Why is this worst case? Because 15 is the lowest. Okay? So I'll write here 15. 15 is the worst case scenario. Okay? WCS is worst case scenario. Now, if player 1 chooses B, then what is the worst case scenario between 40, 10, and negative 30? We know it's negative 30. Why? Because the worst is player 2 will choose 3 and player 1 will lose 30. Okay? And finally, what's the worst case for if player 1 chooses C? Then the worst case is negative 10. Okay? Now, as you can see, choosing the worst case scenario for player 1, let me erase this. Choosing the worst case scenario for player 1 is actually choosing the minimum. Okay? You're choosing the minimum of each row. Okay? Next. After looking for the worst case scenario for player 1, you also have to do it for player 2. So what's the worst case scenario for player 2? So if player 2 chooses 1, then you have the options 20, 40, and negative 10. What will happen? The worst case scenario is player 1 will choose C, and you will get up. player 2, sorry. If player 2 chooses 1, then the worst case scenario is 40. Why? Let me write that, 40. Why? Because in the point of view of player 2, 40 is actually a loss for player 2. So between a loss of 20, a loss of 40, or a gain of 10, the worst case for player 2, if player 2 chooses 1, is 40. In the same way, the worst case scenario for player 2, if player 2 chooses 2, is 15. Because between 15, 10, and 5, 15 is the worst. And finally, for strategy 3, the worst case scenario is 65. Okay? Now, let's go back to player 1. We have these 3 worst case scenario. If you look at these worst case scenarios for player 2, we're actually getting the maximum. You're getting the maximum between 20, 40, and negative 10, 40, 15, 10, and 5, 15, and 15, negative 30, 65, 65. Okay? So for player 1's worst case scenario, you're getting the minimum of each row. And for player 2's strategy, to get the worst case scenario, you're getting the maximum. Okay? Now, in the point of view of player 1, the 3 worst case scenarios, 15, negative 30, and negative 10, what do you think will player 1 prefer? To win 15, to lose 30, or to lose 10? Obviously, to win 15. Okay? Again, for player 1, given that he has 3 possible worst case scenarios, 15, negative 30, and negative 10, what do you think player 1 will do? Obviously, player 1 would like to win 15. And what are we getting? We're getting the maximum of the minimums. Right? You're getting 15, which is the biggest out of the 3. And what are the 3? The minimums. And this is where you have your maxi-min. On the other hand, if we look at player 2, the 3 worst case scenarios are 40, 15, and 65. And in this case, if 40, 15, and 65 are the worst case scenarios, then for player 2, he would rather lose 15 than lose 40 or lose 65. And by choosing 15, 15 is the lowest or the minimum. So what we're actually doing is we're getting the minimum of the maximums. Okay? So 15 is the minimum of the maximums. 15 here is the maximum of the minimums. Okay? This one is maximin. This one I will call minimax. Okay? This 15 actually points to this cell, no? Where player 1 chooses A and player 2 chooses 2. This 15 also points to the same cell where player 1 chooses A and player 2 chooses 2. The maximin and the minimax agrees. Therefore, this is your optimal solution. In fact, this is what we call a saddle point. Okay? Why is this called a saddle point? If you remember a saddle, upuan ng kabayo, diba? A saddle is where it is the most stable point of when you're riding a horse. No? So essentially what we're saying here is this 15 is the most stable decision. Why? Because in the point of view of player 1, that's the best, given the worst. In the point of view of player 2, this is the best, given the worst. Okay? Now, let me now introduce to you the term value of the game. The value of the game essentially is your Z value. And in this case, the value of the game is 15. In the previous example we had, the value of the game is 40. Okay? And if value of the game is equal to 0, then the game is said to be fair. Okay? We don't care about the other numbers. As long as the value of the game is 0, then it is said to be, the game is said to be fair. Okay? So again, player 1, 2 strategies, A and B. Player 2, 3 strategies, 1, 2, and 3. Let's say you have the numbers 40, 10, negative 20, 100, 50, negative 30. Okay? And to use again the technique that I showed you a while ago, quickly comparing strategies, every pair of strategies, higher, lower, so no more. Between 1 and 2, higher, lower, no dominated. 1 and 3, lower, higher, no dominated. Between 2 and 3, lower, higher. Again, no dominated. So, given the last example, let's look for the worst case scenario, the best of the worst. So, what we're looking for is the maximum, remember? And for player 2, the minimax. Okay? So, what's the maximum? You're getting the minimum first, and then you're out of the minimums, you're trying to maximize. So, the minimum here is negative 20. The minimum here is negative 30. The max for player 2, we're getting the maximum first. Between 40 and 10, it's 40. Negative 20 and 100, it's 100. And 50, negative 30, it's 50. Among the minimum, you're trying to maximize. So between negative 20 and negative 30, which points to this solution. Among the maximum, the minimum is 40, which points to this solution. So what does this mean? The maximin and minimax did not coincide to a single cell. No, they're not of the same value. Okay. So what does that mean? That means there is no saddle point. Okay. So what does it mean for a problem to have no saddle point? That means that player 1 and player 2 cannot agree on a decision. Unlike in the previous example where the worst case scenario for player 1 is 15 and the worst case scenario for player 2 is 15, and they both point to the same solution. This example actually shows you a solution where both players, player 1 and player 2, agrees to this solution. However, in this example where the maximin and the minimax does not match, it actually just shows that player 1 and player 2 cannot agree. Now, what I would like to do is I'd like to demonstrate to you why player 1 and player 2 cannot agree. Okay? Now, in order to demonstrate to you this example, I will have to do it in steps. And I will have to change some of the rules of the game. Previously, in one of the assumptions, I said that in order to play the game, each player will have to simultaneously choose a strategy. Okay? Now, let me change that assumption a bit, and I will change it in a way where I will let player 1 choose the strategy first. Okay, so player 1 will choose between A or B first, and then he will tell player 2 what his choice is. Okay, now once player 2 knows the strategy or the choice of player 1, then player 2 will get to choose among his 3 strategies. Now, once player 2 has chosen a particular strategy, then he will have to give player 1 a chance to either agree and stay as is on player 1's strategy, or for player 1 to change. If player 1 decides to change the strategy, and because player 2's current strategy was based on the fact that player 1 chose, let's say, A, and let's say player 1 chose B, then we will have to give player 2 the chance again to change the strategy. And it will go on back and forth, no? Letting or allowing player 1 and player 2 to change the strategy depending on how the other changed. Okay? It will continue, the cycle will continue until we reach a point wherein both players will agree. Okay? Now, so let's try to demonstrate that. Let's say I'm player 1 and let's say I chose A. Now, because player 1 chooses A, if I were player 2, I have the choice between 40, negative 20, and 50. And because I know player 1 will choose A, therefore, so let me write A, therefore, player 2, sorry, this is the strategy for player 1. Because player 1 chooses A, therefore, player 2 would like to choose 2. Okay? But because player 2 chooses 2 and we are now giving player 1 the chance to change his strategy or agree to player 2, then looking at A and B, if player 2 chooses 2, player 1 would rather win 100 than lose 20. And therefore, because of this, player 1 will change his decision to B from A. And because player 1 changed the decision to B, we will have to let player 2 also change his strategy or agree. If player 2 agrees, then that stops the cycle. Then there should be a saddle point. But look, if player 1 chooses B now, then we have these three values, 100, 10, 100, and negative 30. Then player 2 would like to earn 30 instead of losing 100. And therefore, player 2 will change his strategy to 3. Okay? Now, because player 2 changed his strategy to 3, player 1 will also change. Why? Because between A and B, if player 2 chooses 3, then player 1 would rather win 50 than lose 30. And therefore, this goes back to A. And because player 1 chooses A, player 2 will change his solution to 2. And because player 2 changed his solution to 2, player 1 will change his solution to B. And then the cycle will continue. Will this end? No. Will there be an agreement between player 1 and player 2? No. Then that is what we call no saddle point. Okay? So, just to finish this, no saddle point means no agreement between player 1 and player 2. Okay? So, question. If player 1 and player 2 cannot agree on a single strategy, on a saddle point, does that mean there is no more optimal solution to this game theory problem? No. And let me show you how to get the optimal solution later. If a game theory problem does not have a saddle point, it doesn't mean there is no optimal solution anymore. In fact, every game theory problem will always have an optimal solution. However, the optimal solution will just be in a different form if there is no saddle point. What do we mean by different form? Let me show you two different kinds of solutions. Okay, these two are solutions to a game theory problem. However, if you look at this solution, what does this mean? Let's say this is for strategy A, B, and C. This means this solution means that for the player's point of view, he will do strategy A 100% of the time, and do B and C 0% of the time. On the other hand, if the solution looks like this, 1/3, 1/3, 1/3, then what does that mean? Then that means 1/3 of the time, this player should do A, 1/3 of the time, this player should do B, and 1/3 of the time, this player should do C. This kind of solution is what you call a pure strategy. This kind of solution is what we call mixed strategy. Essentially, a pure strategy is a strategy where you do one strategy 100% of the time and all the other strategies 0% of the time. On the other hand, a mixed strategy is a strategy where you do some strategy, some percentage, let's say 1/3, you do a different strategy, let's say 1/3, and then you do the last strategy 1/3. All you have to remember is that in a mixed strategy, the only requirement is for the sum of the probabilities to be equal to 1. So for example, one possible mixed strategy looks like this. 1/2, 1/2, 1/4, 1/4. Why? Because the sum of the strategy is equal to 1. Again, 1/3, 0, 1/6, 1/6, 1/3. This is again a possible mixed strategy. Again, why? Because the sum is equal to 1. So now let's go back to the previous example where we didn't have any saddle point. So let me just quickly write the payoff table. A, B, 1, 2, 3. And this is 40, negative 20, 50. Okay. Now, as I've said, this problem doesn't have a pure strategy. Now, the question now is how do we get the optimal mixed strategy? What percentage should player 1 do A and what percentage should player 1 do B? What percentage should player 2 do 1, 2, and 3? That is our goal right now. So let's focus first on player 1. To understand how to get the optimal solution for player 1, let us do it this way. What if for player 1, okay? What if for player 1 he decides to use this strategy, 1/3 and 2/3, okay? So player 1 will do A 1/3 of the time and player 1 will do B 2/3 of the time, okay? Now, what do you think player 2 should do? Because player 1 will do A 1/3 of the time and player strategy B 2/3 of the time, then if player 2 chooses 1, so looking at this, if player 2 chooses 1, he will either get 40 or 10. He will not get 40. He will lose 40 or he will lose 10. He will lose 40 1/3 of the time. He will lose 10 2/3 of the time. And if you go back to your probability class before, you can actually get the expected value. So expectedly, 1/3 times 40 plus 2/3 times 10, which gives you 20. So expectedly, player 2 will lose 20. Again, why lose 20? Because we're using the numbers in the point of view of player 1. Okay? So that is if player 2 chooses 1. However, if player 2 chooses 2, what will happen? If player 2 chooses 2, then 1/3 of the time he will win 20, 2/3 of the time he will lose 100. So using expectation, that's 1/3 times negative 20 plus 2/3 times 100. That gives you 200 minus 20, that's 180 over 3, that's 60. So expectedly, if player 2 chooses 2 because he knows player 1 uses 1/3 and 2/3 strategy for A and B, then player 2 will expect to lose 60. And finally, if player 2 chooses 3, that's 1/3 of the time he will lose 50, 2/3 of the time he will win 30. So using expectation theory, you get an expected value of -10/3. So what does that mean? That means if player 1 uses 1/3 and 2/3 as his strategy for A and B, and if player 2 chooses 3, in the long run, he will win 10/3. And because player 2 has the choice between choosing 1, 2, and 3, if he chooses 1, he loses 20. If he chooses 2, he loses 60. If he chooses 3, he wins -10/3. Then, obviously, player 2 will choose 3 because he'd like to win 10/3. So again, in summary, if player 1 uses this, player 2 chooses 3. And the value of the game is -10/3. On the other hand, what if player 2, instead of using 1/3 and 2/3, what if he uses 3/4 and 1/4? Okay? Now, doing the same analysis, if player 2 chooses 1, then again, what will happen? Instead of this being 1/3 and 2/3, this becomes 3/4 and 1/4. So using expectation theory, that's 3/4 times 40 plus 1/4 times 10. So that's 3/4 times 40 plus 1/4 times 10. And that is equal to 130 over 4, or what's this? 32.5. If player 2 chooses 2, then he will have the choice between -20 and 100. So expectation theory tells us the expected value is 3/4 times -20 plus 1/4 times 100. Which gives us 10. That's -60 plus 100, that's 40 over 4. And finally, if player 2 chooses 3, we have 50 and -30. So that's 3/4 times 50 plus 1/4 times -30. That's 150 minus 30, 120. That gives you 30. Okay? And again, because player 2 has the control over what strategy he will choose, he can either choose 1, 2, or 3. If the expected value is 32.5, 10, and 30 respectively, then player 2 would like to lose 10 instead of losing 32.5 or 30. Okay? So to summarize, if player 1 does this, 1/3 and 2/3, then player 2. So again, if player 1 uses 1/3 and 2/3, then player 2 will always choose 3. And the value of the game equals -10/3. However, if player 1 chooses 3/4 and 1/4, then player 2 will choose 2. And the value of the game is equal to 10. Now, if I'm player 1, and I'm looking at the two possible scenarios, if I do this, if I do 1/3, 2/3, I will lose 10/3 in the long run. If I do 3/4, 1/4, I will lose 10. I will win 10. Sorry. So if I choose this, I will lose 10/3 in the long run. If I choose this, I will win 10 in the long run. So if I'm player 1 and I'm comparing the two, what will I do? 1/3, 2/3, or 3/4, 1/4? obviously, between negative 10 thirds and 10, I'd rather get 10. And therefore, eventually, P1, if the only possible decisions for P1 is to either do 1/3, 2/3, or 3/4, 1/4, is to do 3/4, 1/4. And to get the value of the game to be equal to 10. But the question now is, are these two decisions or strategies, are these the only available strategies for player 1? Is the only available, are the only available strategy for player 1 1/3, 2/3, or 3/4, 1/4? Can it be, for example, 1/6, 5/6, or let's say 7/8, 1/8, or some other pair of probability or fraction, as long as the sum of the two is equal to 1? Isn't these other strategies also available? Aren't these other strategies also available to player 1? So the question now is, why are these two the only possible solutions I'm presenting? I'm presenting to you these two possible solutions just to show you the dynamics of what player 1 and player 2 will actually decide eventually. If these are the only two possible decisions, then player 1 will choose this. Why? Will choose 3/4, 1/4. Why? Because player 1 would rather win 10 than lose negative 10 thirds. But remember, in this case, player 1 in fact has infinitely many possible solutions. No? One other possible solution is 1/6, 5/6, 7/8, 1/8, or some other pair of probability, as long as the two is equal to 1. So the question now is, how do you look for that pair of probabilities that will net you, or net player 1, the highest value of the game? If we're just comparing the two, the highest is 10. But out of the infinitely many possible probabilities or strategies, how do you look for that pair of strategies that will give you the highest value of the game? And that is where we will be using linear programming.